Greetings. Now, if you're coming off the last two videos in this series, you may just be chomping at the bit to learn how to get the elusive instantaneous velocity for graphs that don't have nice polygonal shapes. In this video, we are going to be running through a crash course on a fundamental calculus concept, the derivative. So firstly, let's officially define what a derivative is. The operation of differentiation is a mathematical operation that acts on a function y equals f of x. The result is called the derivative, officially, of f of x, and it is also generally notated as y dot equals f prime of x. Now, you're probably wondering about that funky notation for the functions at the bottom there, but sit tight and we will cover it later in this video. Okay, so a derivative effectively gives the slope of a function f of x at a given value of x. It also represents the rate of change of a function f of x at a particular value of x. Now, to visualize this, notice the figure on this slide showing the two magnified sections of the quadratic function given. Now, if you look really closely at the quadratic function, as shown from these magnifications here, eventually the curvature of the function becomes negligible, and there lies an effectively linear line that has a slope associated with it from these two spots here. Zoom out and think that this curve is made up of millions and millions and millions of lines, all with their own slopes. So a derivative kind of zooms in to one of those lines and finds the slope of it in the same way that you would find the slope of a linear function. So in essence, derivatives are no different from how you already find the slope of a line. With the slope formula, it takes 2 points to establish a line and calculate a slope. And generally, the way that we're going to be thinking about it going forward is that to find the slope at a single point, xy, on a function y equals f of x, like we have over here, we choose another point that's just slightly ahead by some interval, and we'll refer to that as the coordinates x plus delta x and y plus delta y, respectively. So a position plus some displacement for each direction. Now, that was a lot to unpack, so we're going to take a step back and do a quick history lesson so that you can see how intertwined physics is with this concept. I love this story, so I'm really excited to share it with you. So we're going to think about just a falling object here, and we're going to put ourselves back into the past where we don't have a lot of our fancy technology. Now, even in a lot of the labs that you've probably done, I'd say it's not just you. That early physicists, especially without handy tools like stopwatches or, oh boy, video analysis, slow motion, photo gates, we have such nice stuff now. These early physicists had quite a bit of trouble finding the exact velocity of an object at a certain point in time, which seems kind of silly now that we have things like speedometers and such. Now, because of this, a lot of them sought a solution that made use of the mathematical models that were being applied to motion at the time, which was a very new concept. So we're going to start with this joyful fellow over here. This is Galileo Galilei. And one of his experiments saw data collected for how much a falling object displaced in different intervals of time. You can see a small subset of this data right here in this table. Now, eventually, this data contributed to the creation of one of the kinematic equations modeled by y of t equals 16t squared. This probably looks pretty familiar to you, sans the 9.8 or 4.9. Now, if you wanted to find the velocity associated with this object, the best you could really do at the time was estimate the average velocity of this object during an interval of time, like say 1 second. Now, in the 1500s, even this time interval was generous for finding something like position or displacement, because again, modern timing technologies were not really readily available. So it took some clever engineering of experimental designs to get good data like this. So a problem arose. Like, what if you wanted to find the velocity at exactly t equals 3 seconds? What could you do? And so, while a lot of attempts were made to study and address this issue, including better measurement techniques, of course, it was our boy Isaac Newton who had a rather controversial idea. He suggested using an infinitely small, almost hypothetical number called an infinitesimal, which generally is written or symbolized as a lowercase d next to whatever quantity was intended to be infinitely small. In this case, time, so dt. His idea was to make use of the average velocity technique that we already had, but use the infinitesimal dt for the interval of time so that the velocity or the slope would hardly have any time to change between the 2 points, thus giving us one definitive value as opposed to an average between 2 very different slopes. So to try this out, we're gonna write out the position of the object for 2 moments in time, one being just an infinitely small step up from the other. Now, as I write this out, you end up with a quadratic that you need to expand out here. So I went ahead and did that here for convenience's sake. So if we write out the average velocity formula, we've got our final position minus our initial position over this interval of time, dt, which is, again, infinitely small. Now, if we substitute everything in, we notice that we have a 16t squared that can be canceled out here. So we'll go ahead and eliminate that. And what we're left with is 32t times dt plus 16 times dt squared all over dt. And this is where the cool part happens. Remember that dt, according to Isaac Newton, is technically a number. It's not just this thing that's stuck there. And because it's a number, we can treat it like a number and do our usual mathematical operations with it, including a sploinky, which every single term in this equation has. So we can get rid of dt, except for this one right here that's attached to the 16. And so what we're left with is, there's a bit of an error there. That should not be a dt squared. Whoops. We're left with 32t times 16 dt. And this is pretty much there. We have an equation now for velocity that's just in terms of one specific moment in time, which is awesome. However, we also have this infinity term that's in here too, or 1 over infinity technically. And that's kind of a problem, because how the heck are we supposed to know exactly what infinity is? It's a hypothetical. And so Newton made a controversial move to simply obliterate it from existence, arguing that 1 over infinity would just be so small compared to the velocity that 32t calculates over here that it would just simply be negligible. Now, this move angered a very, very, very large number of mathematicians, and that was a battle that raged on for centuries. But despite their protests, Newton's method stuck, and voila, the derivative was born. So in a double whammy, this resulted not only in the invention of calculus, but it also gave us a new kinematic equation. Because if we look at our functions here, we've got 16t squared transforming into velocity equaling 32t. If we generalize that a little bit, then we'll notice that our position function is basically 1/2 at squared, and that's transforming into another kinematic equation, vt equals acceleration times time, which would eventually be known as v of t equals v naught plus at squared, or the Vogt equation. And so on the calculus front, after generalizing everything and making sense of infinitesimals from a couple of other folks, we got the definition of the derivative, which is given in terms of a limit, which was a good way to kind of quell the anti-infinitesimal crowd. This is a formula that I'm not really going to delve into too much on the physics front, but this is something that you're going to learn about and become very familiar with in your calculus class. So I will let that delve into the details there. Now, on the physics front, or just on the mathematics front in general, after people started playing around with the derivative method a little bit, they started to notice a lot of different patterns that could be established as rules, as it seemed to be valid enough, or it made logical sense. One thing that made logical sense was this first one, the constant rule. The constant rule simply says that if your function is a constant value, which is we're defining as c, then the derivative of that function, f prime of x, is going to always equal 0. Now, the reason this makes logical sense is because, well, it's a constant value. It has no rate of change. And we said earlier that a derivative is finding the slope or the rate of change of a function. So if it's a constant value, it's not going to be changing. Or in other words, it's a flat line, which is going to have a slope of 0. So the constant rule is a pretty good one to fall back on, and it also leads to a fallback for a couple of the other rules we're going to be using later. So for example, if f of x equals 32, then f prime of x is going to equal 0. Now another rule or another pattern that people started to pick up on was the addition and subtraction rule. This is saying that if, say, y equals f of x plus or minus g of x, so you have like one function and you're adding it to another function, then the derivative of y with respect to x is just going to be the sum of those two functions, of the derivatives of those two functions taken individually. So you would take the derivative of f of x, you would take the derivative of g of x, and then you would simply add them or subtract them together, just as you would have for the function y. So for example, let's say our function f of x is 16x squared plus 32. Then f prime of x would be the derivative of 16x squared, which we established was 32x, plus the derivative of 32, which by the constant rule would be 0. And that would be our derivative. And finally, what about like coefficients out front of functions? That's given by the constant multiple rule. And this says, like, say, hypothetically, we have y equals c, some constant, times a function f of x, where c is a constant. Then the constant multiple rule says that the derivative of y with respect to x is just going to be that constant times the derivative of your function f of x. So in other words, the constant out front of a function has no bearing. It plays no role on what the derivative is at the end of the day. So for example, say we have the function 16 times x squared, then the derivative of that function is going to be 16 times 2x, where, as we're about to find, the derivative of the function x squared is 2x. Cool. Nice and handy. And so while this was going on, people also started to pick up on shortcuts for certain derivatives of certain types or archetypes of functions. And so the first one here is the power rule. This is your bread and butter. This is what you're going to be doing most of the time in physics, at least. And this is given by a general format c times x to the n. So it would be something like 1/2 x squared, let's say. And I want to point out this d over dx thing here, this format right here. This d over dx is generally called a derivative operator. This is almost like a command saying I'm applying a derivative to this function within the brackets. So when you apply a derivative to this function, the output of that derivative machine is you take the n, you multiply it out front next to the c, and then whatever exponent you had, x raised to, you'll subtract that by 1, where c and n should both be constants in this case, and n cannot be 0. If n is 0, then you have a constant value, and effectively that just becomes the constant rule from before. Okay, so for example, say we have the function 16 times x squared, and we do a derivative of that function. Then using the power rule blueprint over here, I'm going to multiply by n, and then I'm going to subtract the exponent of my x by 1. And so we'll have 2 times 16 times x raised to the 2 minus 1. And after we simplify things a little bit, we'll have 2 times 16 is 32, and then x raised to the 2 minus 1 just becomes x raised to the 1, so we get 32x as our derivative. Again, you might take a little bit of practice with this. We're going to do a bit of practice in a moment, but this derivative method will become your bread and butter, and it'll come naturally to you in a jiffy. So just stick with it and just follow the blueprint, worst case. All right, a couple of other ones are, the trig functions are pretty notable in how their derivatives relate to each other. And that's because if you take the derivative of, say, a sine function, it actually just transforms into a cosine function. And if you plot these two overlaid on each other on Desmos, you can start to see why if you pay attention to their slopes. So the derivative of sine x is just cosine x. And if you take the derivative of cosine of x, that transforms into negative sine of x. So that negative sign is important. Please don't forget it. And finally, there are also shortcuts for derivatives of exponential and logarithmic functions. For instance, the derivative of natural log of x is 1 over x, or the reciprocal of x. And the derivative of e to the x is, well, e to the x. It doesn't change. It's immutable. That one's always really nice to have. Now, all of these derivatives, all of these rules are given to you on the AP Physics C formula sheet. That doesn't mean that you shouldn't memorize these, because anything that you memorize is time that you save from having to look at the formula sheet to begin with. But do know that they are always there, and I highly implore that you always be referencing that while you're practicing and getting used to these new operations. So speaking of practice, let's go ahead and delve into that, shall we? All right, so we're going to do a couple of example problems. I have a pretty good assortment of different derivatives here that just give you a sense of the sort of derivative that you're going to be taking in this class, which largely consists of power rule and a little bit of trig functions here and there. So this first one is pretty much just straight up power rule. It's f of x equals 4x cubed. And so to start out, we're going to just consider exactly what operation we need to do with the power rule again. We're going to take this exponent and we're going to mark it down by 1. And then whatever exponent we had here in the first place, we're going to carry over and multiply with this 4 here. So that's going to be 3 times 4x, and then 3 minus 1 is going to turn into 2. And so f prime of x, let's say, is going to equal 12x squared for this first derivative. Nice and simple. This next one I have in different terms. This is more likely to be the format that you see most functions that you're differentiating in this class taking, which is a position function with respect to time, t. Although here, t is just, again, any arbitrary old variable. And here we really just have a big chain of problems like our first one over here. And so the only extra rule that we're going to be applying here is the addition and subtraction rule, which really just tells us that if we have a chain of functions that we need to take the derivative of, we really just take the derivative of each of those functions individually and continue to add them all together at the end. So we're going to follow again with the same power rule over here. So I'm going to say x prime of t, t to the fourth. Again, we're going to do 4 minus 1 and then bring down the 4. So that will become 4t cubed. Plus, we're going to, again, multiply the 3 by this 2 here, and then bring this 3 down by 1. So that's going to become 6 times t squared minus, and again, bring down 2, subtract 2 by 1. So it'll become 2 times 4, which is 8 times t to the power of 1, just for clarity's sake there. T to the 1 is going to be subtracted by 1 and multiplied, and we're going to multiply this 3 by 1 over here. So that'll be 1 times 3 times t to the power of 0. So for clarity's sake, I'll keep that 3 times t to the power of 0. And then any constant, we're going to apply the constant rule, which says that if f of x is a constant, like 7 is here, then that equals 0 over here. So we'll just make that 0. And really just to rewrite everything, it'll be 4t cubed plus 6t squared minus 8t plus 3 times 1, because anything to the power of 0 becomes 1, and then plus 0, we don't really need to write that, so this is our derivative function right here. Cool. Now this next one looks absolutely horrifying, and I will be the first person to admit that. However, don't let that intimidate you. Usually radicals have a tendency to do something like that. So I'm going to show you how you should really approach radicals for derivatives most of the time, and that's to turn them into regular old exponents like everything else would be. That's because a radical really is just something raised to the power of 1/2, or for the second term over here that's a cubed root, it's raised to the power of 1/3. It's always 1 over whatever the power of that specific radical or root is. So I'm going to rewrite this function before we take the derivative of it. I'm going to say y equals, this is going to be x to the power of 1/2 plus 4 times x to the power of 1/3 minus, this next one is 2 over x. Anytime you have an x in the denominator, that just means it's x to the power of -1. Anything with a negative power goes into the denominator. So it'll be 2 to the power of x to the -1. Or sorry, 2 times x to the power of -1. And then lastly, plus 1 over 3x squared. I'm going to rewrite that as 1/3 times x to the power of -2. Just so everything is in the exact same format that we need to, again, apply this power rule up here, our handy dandy tool. So now that we have everything in this format, we can go ahead and take the derivative. So I'm just going to say y prime is equal to, we're going to take down this 1/2 and then subtract 1/2 from 1. So that will be 1/2 times x to the power of 1/2 minus 1 is 1/2 minus 2 over 2. That will be -1/2. plus, we're going to take down this 1/3. So it'll be 4 times 1/3, or 4 over 3, times x to the power of, well, it's going to be 1/3 minus 3 over 3. So it will be negative 2/3 for this other exponent here. Again, that would have been really ugly with radicals. So using exponent form is pretty nice here. Then minus, well, okay, I'm going to keep this in a minus, but I'm going to put this term in parentheses, and you'll see why in a second. I'm going to take down this -1, so it'll be -1 times 2 times x to the power of -1 minus 1, so that will become -2. All right, be careful with negative signs here. And then finally, this last term here, it's kind of the same thing. We're going to do plus, and then just for clarity's sake, I'm going to keep this in parentheses. And I'm going to take down this -2, so it'll be -2 over 3, once we multiply that all out, times x to the power of -2 minus 1, that will be -3. Okay, now that we have all that laid out, let's pay close attention to our signs here. This is going to stay positive, this guy's going to stay positive, this fella is now going to become positive because we're subtracting a negative term. And then this fella over here is going to become negative because we are adding a negative quantity now. So in the end, we'll end up with y prime equaling 1/2 x to the power of -1/2 plus 4/3 times x to the power of -2/3 plus, now pay attention, 2 times x to the power of -2 minus 2/3 times x to the power of -3. This one is probably the ugliest out of this selection, so it's all downhill from here. Now, one thing to note is that you absolutely can simplify this back into the nice compact radical form that we had to start with, because a lot of these can be simplified to radicals or into denominators. I'm not going to do that here for the sake of time, and for the record, AP generally does not care about how much you simplify something. So sometimes it is a little bit easier and quicker to just leave it in whatever ugly form you have, as long as it is correct. All right, and finally, a little bit of trig. This is x of t. So again, position as a function of time, equaling this combination of trigonometric functions right here. So in this case, we're going to be implementing some of those common derivatives of trigonometric functions, namely sine and cosine respectively. And here, we don't really have any powers to worry about, so we're okay with that. And so all we're really going to do is take the derivative of sine and cosine respectively. It's pretty nice. So in this case, we have 6 times sine of t. Now we can't apply the constant multiple rule here because the 6 really has no bearing on the derivative of sine overall. So we'll just keep that 6 out, and we'll take the derivative of sine of t, which will be cosine of t. So 6 times cosine t for that first term. And now, again, we're following the addition subtraction rule here. We're just going to treat this as its own derivative, separate from everything else, where this minus sign is technically also separate from everything else. And we're just going to do the same thing here. I'm going to keep this in parentheses so we know it's a separate thing. This 2 is, again, by constant multiple, a completely separate thing. So it'll be 2 times the derivative of cosine of t, which is negative sine t for our case. Now we have minus a negative quantity once all of this gets multiplied out within the parentheses. So our final derivative function will look like 6 cosine of t plus 2 times sine of t. So it went from 1 positive, 1 negative to both positive. Pretty nice. All right, and every derivative you find in this class is pretty much going to follow something close to this. There are a few exceptions to that. Sometimes things get a little bit more complicated, and that's what we're going to focus on next with this next rule. All right, this next rule is a fun one. So sometimes functions are embedded within other functions. You will see that from time to time. It doesn't happen super often in physics, but it's good to be prepared just in case it does happen. And it turns out a shortcut and rule was determined for this situation as well. So the chain rule is stated as, like, say we let y be a function of f, which itself is a function of g. So in other words, y equals f of g of x. Then the derivative of y is given by dy over dx equals f prime of g of x times g prime of x. So you take the derivative of the outermost function and still embed g of x within that one. And then you multiply that by just the derivative of the innermost function here, which is g of x. So in a sense, it's like a chain reaction. You're like taking the derivative of this and taking this out, taking the derivative of this, and so on and so forth. And it also turns out that this method does chain together quite smoothly. So for instance, say I wanted to be particularly evil and give you like 4 embedded functions, each within each other like I have here. So if y is a function of f, which is a function of g, which is a function of h, which is a function of k, the chain rule still works the exact same way. So here, if we wanted to take the derivative of that, you would take the derivative of f and embed everything else unchanged within it, multiply that by the derivative of g, and embed everything within g inside of that unchanged, then multiply by the derivative of h with k of x embedded within, and then finally k of x just has x inside of it. So you would just multiply by the derivative of k of k, and after that you've got your full derivative. So that's particularly gross. I will never really give you something that crazy, but in your calculus class, all bets are off. So with the chain rule, let's go ahead and do some practice. All right, coolio. So let's try this thing out. I have the chain rule up here for reference so we can follow it even if things get really crazy like this last one here. But we start off pretty nice and simple. Now the way I'm going to write this out is I'm going to explicitly write what the f of x function and the g of x function, or anything that follows after that, are before we actually go through with applying the chain rule. This is just for clarity's sake, so that you can learn, but over time you're going to feel like the chain rule becomes more and more natural, and eventually you won't really need to worry about that. So if you like this, or you feel already pretty good about how the chain rule is applied, don't feel obligated to do this, but I am going to do it just so it's very clear what's going on with each of these examples. So our first function is y equals sine of x squared. So we have an x squared function embedded within a sine function. And how I stated that is how we're going to treat the chain rule here. So first off, our f of x function is generally the most like fundamental one. It's the one that's like furthest on the outside, like you see here. And because one function is embedded within another, the one that's, I guess, embedding the other function is f of x, and that's going to be sine in this case. And I'm just going to write that as sine of x. We'll have all the proper assignments later. All right, and then the function that's embedded within sine, or g of x, is x squared, and that's a power function. So we're going to be applying power rule to that one. All right, and now that we have both of our functions, let's go ahead and take the derivative of y. So we're going to do, say, y prime is, well, dy of dx, another way to write it, is going to be the derivative of f, and then g of x is embedded within it. So derivative of f of x is, based on our previous knowledge, going to be cosine of x, if you want to check your reference tables. So it'll be cosine of, and then we can't forget that we have to still embed g of x within this one. So it'll be cosine of x squared for this first one. And then next, we have to take the derivative of just gx alone. So we're going to multiply that by the derivative of gx, which will be, if you apply power rule, 2x. You take the 2 down and then subtract 2 by 1. And this, in its most unsimplified state, is the derivative of our first example. Cool. This next one pretty much just pulls the switcheroo. It's the same thing, but now x squared is the primary function and sine is now g of x. That's because we're saying verbally that sine of x is embedded within x squared. So f of x now is x squared, and then g of x, the thing that's being embedded within f of x, is sine of x. And again, our actual function is a bit more complicated than that. There's nothing that explicitly says x squared in this function, but I'm just using x here as a way to show the fundamental function that's at play there. All right, so now let's take the derivative of this one, see how things change. So in this case, we're going to need to take the derivative of x squared first. The derivative of x squared is 2x. So it's going to be 2 times, and then embedded within 2x is our g of x function. So it'll be 2 times sine of x for this first one. It gets a little weird sometimes, but as you start to wrap your hand around it, it starts to feel a bit more natural. And then multiplied by that, now that we've done this stage right here, is we just take the derivative of g of x. In that case, it's just sine of x. So we're going to take the derivative of that, and we'll get cosine of x for that second. And that is our derivative of our second example. Again, nice and easy. And just for clarity's sake, before we move on to a bit of an ugly, gross one, again, I'm going to clarify that this part right here is f prime of g of x right here. And this part right here is just g prime of x when we're thinking about how the chain rule is explicitly stated. And again, same thing over here. This is f prime of g of x right here. And then this is g prime of x alone right here. Cool. All right, now let's look at a really gross, ugly one. This is 3 functions embedded in one. And thank goodness we thought through a really like the worst case scenario for this already. So we can still follow this blueprint. We won't really need to do the mental gymnastics again. So in this case, we have 3 functions. So we need to, I'd say again, write those out. And generally, again, it's going to go from the outside in for f of x through, z of x. So f of x here is going to be our sine function. Then it stands to reason that natural log is going to be g of x. And then cosine of x is embedded within everything else. So that is going to be our last function. We'll call that, well, what does it say over here? H of x. So f of x is our outermost function. That's going to be sine x. G of x is our next outermost function. So that's going to be natural log of x. And then finally, h of x is cosine. So we'll make that one our last fella over there. All right. Now we can officially begin our derivative. So we're going to say y prime equals, prepare yourself. We're going to need to do f prime of everything else embedded within. So we're just going to take the derivative of sine x and then embed everything else in, no matter how gross that looks. So it's going to be derivative of sine x, which is cosine of natural log of cosine x. And then we close our parentheses. All right, step 1 complete. Next, we do the same thing, but now we just throw out f of x. We don't need to worry about it anymore. So we're going to take the derivative of g of x and then embed cosine x still within it. So over here, the derivative of natural log of x from our table of derivatives earlier is 1 over x. So we're going to multiply this by 1 over cosine of x, which is embedded within that function still. All right, that's step 2 complete. And now we just need to worry about step 3, which is taking the derivative of h of x by itself. Now the derivative of cosine of x, h of x, is negative sine. So we just need to multiply that by negative sine of x. And that's all she wrote. So again, just for clarity's sake, because that one is pretty nasty, it's a worst case scenario. Again, this is f prime of g of h of x. This one is g prime of h of x. And then finally, this one is just h prime of x by itself. So again, we're just following the chain rule explicitly there. Now, I said earlier that you don't really need to worry about simplification, but in this case, I can't help myself. I love trig identities. Sine of x divided by cosine of x is tangent of x. And that's a nice simplification to make. It just feels very satisfying. So I'm going to just rewrite this as cosine of natural log of cosine x. Not much we can do about that term, but we can multiply this by a nice crispy, well, I kind of forgot the negative sign. I'll put that out here. A nice crispy tan x, just to shorten things a little bit. Not much, but it's honest work. All right. And so that's chain rule. You won't need to apply it too much in this class. It'll happen a lot more in your calculus class. I can guarantee that, but it is still possible that it'll come up from time to time. So good to know. Good, almost done. All right. So another concept I think is rather important to go over for this class is second derivatives. And this concept is pretty straightforward because it just utilizes stuff that you already have. So the second derivative of a function, like it says on the tin, is noted by f double prime of x, or d squared over dx squared for the operator. And it is the rate at which the rate of change of f of x changes. So in other words, it's a rate of change of a rate of change. In physics terms, I know you are dying for that. Let's say that we want to find the second derivative of position. That would be the rate of change of the rate of change of position. So it would be the first derivative of velocity, which itself is the first derivative of position. So if we're finding the first derivative of velocity, we're finding velocity's rate of change. That turns out to be acceleration. So the second derivative of position is the first derivative of velocity, and that is acceleration. Now, this can keep going. And so a position does also have a third, fourth, fifth, and sixth derivative that all have names. The third derivative of position is known as jerk. And it's not really used in a high school physics class, but it can be used for violent motion, such as rocket launches and things where you have such high rates of change of acceleration specifically that it is not negligible. You have to consider it for safety reasons. And my favorites, the fourth, fifth, and sixth derivatives of position, are known as snap, crackle, and pop, respectively. These were published in a paper largely as a joke, but snap has been used before, and it has another name, jounce, that I think is used more often for that. You can find the Wikipedia page on them if you like. All right, so with second derivatives, let's do a couple of examples. All right, and for our last example for this video for now, we're going to focus on just an example of a second derivative. Now, in this case, our second derivative that we're going to be taking is of the function x of t. So again, position versus time equals t cubed minus 27t. So first we need to find the first derivative before we find the second. So in this case, we're just going to do what we've been doing this whole video. We're going to say x of t x prime of t equals, we're going to take the 3 down, 3 times t, and then 3 minus 2, or sorry, 3 minus 1 is 2. So 3t squared for our first term, minus, and then here, all we really need to do, anytime you see a t without, or a t or an x or whatever, without an exponent, is really, that's just going to become 1. So it will become 1 times 27, or just 27. All right, that's our first derivative. So now, get this, all we really do is just take the derivative of this again. So our second derivative, or x double prime of t, is going to equal, we're going to take the 2 down, so it'll be 2 times 3 times t, and 2 minus 1 is 1, so t to the power of 1. And now this fellow right here is now a constant. So if we're applying the constant rule, this whole thing is now going to just blanky out or annihilate to 0. It doesn't matter anymore, so it'll just be plus 0. So if we just want to simplify things a little bit, it'll be 6 times t power to the 1, really just becomes invisible, so it's just 6t, and 0 is 0. So our double derivative x double prime of t is just 6t. Now, what does this mean? Well, if this is a position versus time function, we take the first derivative, which is the function that gives us the rate of change at every time t along this thing's motion. Now, if we take the derivative of velocity, we're getting the rate of change of velocity at every point along this thing's motion. So this right here is an acceleration function. It's showing what this thing's acceleration is going to be at every time t throughout its motion. And this is showing here that the acceleration is steadily or linearly increasing, which is a situation that is kind of taboo. We're not allowed to look at it really in non-calculus based physics, but it is totally normal and we can worry about it in this class, which is very exciting. All right, so that's a second derivative or a double derivative. And again, normally that's going to be for finding something like acceleration for physics. So cool beans. All right. And to round things out, I want to actually clarify a lot of the different notations that exist for derivatives, because in this class, I'll try to stay as consistent as possible with what notation I'm using. But as you go forward into future careers, future classes, all sorts of things, you're going to see a lot of different people with a lot of different preferences for how they like to write these things. So I thought I would introduce all of them to you just in case, so you never look at something and say like, what the heck is that? So I'm going to focus on 3 specific notation forms. The first one is differential notation. The second is dot notation. And the third is prime notation. You have seen all three of these within this presentation today. So instantaneous velocity, I'm going to focus on those. In differential notation, that's the d over d format. So velocity, for instance, is dx over dt, or in some sense, you could call it change in x over change in t, just over very small intervals, like you saw on that picture earlier. In dot notation, the velocity would be categorized as x dot. You see this a lot in something called Lagrangian mechanics that is used at the collegiate level for physics. And the dot here tends in physics especially to only be used in the context of time. So you won't really see dot notation used as much for other derivative terms besides time. And finally, prime notation is the little apostrophe that you stick next to the function. So the derivative of velocity would be given as x prime of t, for instance. This is helpful if you just kind of want to keep it nice and clean with how you're writing your functions and making it clear that x is a function of t specifically. Now for acceleration, we can refer to it as dv over dt as the rate of change of velocity with respect to time. But that it can also be referred to as d squared x over dt squared. And that would be referred to as the second derivative of position with respect to time. Don't ask why the squareds in the numerator versus denominator are in different spots. I actually don't know. That would be worth investigating. If you find something on it, leave it in the comments. I'm kind of interested to find that out myself. All right. For dot notation, it's either single dot or double dot. Nice and simple. So acceleration could be referred to as the first derivative of velocity, so v dot, or it can be referred to as the second derivative of position, or x double dot. So nice and clean, nice and simple. If you like to go for brevity, this is probably the one for you. And finally, with prime notation, acceleration can be referred to as the first derivative of velocity, v prime of t, or the second derivative of position, x double prime of t. Also good for brevity. So at that point, it's just a matter of preference. So these are all the representations you can kind of expect. I won't try to go too much past these. So use the one that is your personal favorite. I will not judge. I understand all of them perfectly fine. And that pretty much does it for our calculus review. I hope this video was helpful. I apologize for the length, but having these tools available to you up front is going to do wonders for your physics future in this class. So I hope this video was helpful. Please study it over and over. Make sure this stuff is as second nature as it can possibly get, and you will do great, I promise. So thank you for watching, and I will catch you in the next video. Peace.